Welcome to my presentation on removing cost volumes from optical flow estimators. I'm Simone Kiefhaber, and this is a joint work together with Stefan Roth and Simone Schaub-Meyer. Optical flow is the task of estimating the apparent motion between two consecutive frames, and it is often used as an intermediate result or input modality for downstream applications such as video frame interpolation, 3D reconstruction, or unsupervised panoptic segmentation. We need efficient optical flow methods, especially when using them as input modalities for other models. When plotting the required compute operations at various input resolutions for state-of-the-art methods like CRAFT, we can see a steep increase in compute operations when increasing the resolution. The same trend can be observed when measuring the required memory and inference time. As we can see, when we go from HD to Full HD, which doubles the number of pixels, we require 4 times more memory and 3 times more inference time. Due to this reason, running most methods on high-resolution images is currently not feasible without downsampling them. We do a more detailed breakdown of the compute operations by measuring them per building block of CRAFT. The context and refinement networks both scale favorably with respect to the resolution. But the feature network, consisting of the feature extractor and cost volume, scales poorly with respect to the input resolution. This observation motivated us to look into how to make the feature network more efficient. When we tried to optimize the feature network's architecture, we made an interesting observation during a failed experiment. When we trained our improved network, we saw a steady decrease in error. But when we analyzed the quality of the cost volume by mapping the cost volume into an approximated optical flow, we observed that the cost volume was getting more accurate at first, but after some time of training, the error started increasing, while at the same time the overall network's error was still decreasing. This made us wonder how this network could still achieve good accuracies even though the cost volume did not contain useful information anymore after training. This brought us to the question, do we even need cost volumes? In our paper, we proposed the following training protocol to remove cost volumes from optical flow estimators. We start our training with an unmodified CRAFT network, where we first train only on the tartan air dataset, followed by training on the flying chairs dataset. After finishing the training on flying chairs, we reach a point that we call the cutoff point. At that point, we modify our trained network such that the feature extractor and cost volume are removed. Afterwards, we continue by training on flying things and finally on a combined dataset made out of flying things, Sintel, Kitty, and HD1K. This training strategy reduces the endpoint error compared to training a network that does not have a cost volume from the beginning. However, there is still a noticeable accuracy gap between our method and state-of-the-art methods. The key question is now, how can we close this accuracy gap? To close the gap in accuracy, we use some of the freed-up compute budget to use stronger backbone as the context network, shown here in blue. And to test even faster backbones, we also trained a more lightweight backbone, shown in red. We call our method Recover, and our different models are named CX, RN, and MN, corresponding to the used context network, namely ConfNext, ResNet, and MobileNet. They offer different trade-offs between accuracy and complexity. Notably, Recover CX outperforms the state-of-the-art method CRAFT on the Spring dataset. In comparison to other methods, the increased memory efficiency of our methods allows us to run optical flow estimations even at high resolutions, like 4K, with memory footprints ranging from only 3 to 5 GB. When we look at qualitative results, we can see the similar prediction accuracies of CRAFT and our method Recover CX in most areas. But when looking into details, we can see that Recover CX is better at disentangling complex motions. To summarize this presentation, we have shown a simple training procedure that completely removes the cost volume from an optical flow estimator during training. We have proposed 3 different methods utilizing different backbones to create multiple trade-off options between inference time, memory requirements, and accuracy. And our best model reaches state-of-the-art accuracies.